Okay, good afternoon. Today we'll be looking at operations on functions, difference, quotient, and composition of functions. By operations on functions, I mean the traditional real number operations of addition, subtraction, multiplication, and division. Okay, so it is working, right? Okay, I won't speak too loudly. I'm used to speaking loudly. The past few times I think I didn't use this right. Tony may have used his, but I didn't use mine, so I don't need to be yelling at y'all. Anyway, operations. We're looking at addition, subtraction, multiplication, and division. It's the same operations that we perform on real numbers. And the thing to know about these operations on functions, it's basically just algebraic addition, subtraction, multiplication, and division. You know how to add and subtract algebraic expressions. You combine like terms. Or if you have fractions, you get common denominators and add or subtract them. So addition and subtraction is just algebraic addition and subtraction. Likewise, multiplication is just algebraic multiplication, and division, algebraic division. And so to illustrate that, we'll start off with the problem. It's pretty straightforward. This is number 1.
You open it up, 2 plus 2.
It's not that easy, Jacob. Okay. This is number 1. Let me write the problem down. We have f of x is equal to negative 5x plus 3. And we have g of x. G of x is the function 4x minus 5. So oh, wait a minute, I think I miscopied something here. That's just f of x is equal to 5x plus 3 and 4x minus 5. We want to find f plus g, f minus g, f times g, and f divided by g. They want us to give the domain of these as well. So let's just find the sum, difference, product, and quotient, and then we'll discuss the domains, okay? Starting off, f plus g. To add two functions together, you just take the function f of x and you add it to g of x. And we know what f of x is. We know that f of x, we were given f of x, that's 5x plus 3. And I'm going to enclose that 5x plus 3 in parentheses just to make the point that that's all coming from that one function f of x. Plus, now we want to add g of x. Well, we know that g of x is defined by 4x minus 5. And I'm going to enclose it in parentheses just to make the point. Those terms are g of x. These two terms are f of x. Now these parentheses I wrote are unnecessary. When you look at these parentheses, there's nothing there in front to distribute. It's just like distributing, multiplying 3 by 1. So it's unnecessary. And I'll just write it down as 5x plus 3. Now the second set of parentheses, it's preceded by another plus. I think this is an unnecessary set. Now, in a moment, when we're subtracting, we'll have a minus in front of those parentheses. What do you do when you have a minus in front of the parentheses? Okay, go through changing the signs, I agree. So, in a moment, it won't be an unnecessary set. But here, for the first problem, the second set's unnecessary. Distributing a positive 1 changes nothing. So I'll just write down the plus 4x minus 5. And as I said, addition of functions is just algebraic addition. We know how to combine these terms. We combine the x terms. 5x plus 4x. What's that going to give me?
9x.
So we have a 9x
minus 2.
Okay, combining the constant terms. Positive 3 minus 5 gives us a minus 2. I think I'll find f plus g, f minus g, f times g, and f divided by g, and then I'll patch in all the answers, okay? Now, f minus g, we're subtracting the functions. That's just the first function, f of x, minus g of x. F of x, we've already said that's 5x plus 3, and I'm going to enclose it in parentheses just to make the point. Those two terms came from the function that gave me f of x. Minus
parentheses 4x minus 5 plus c.
Well said. The first set of parentheses, there's nothing in front, so we just drop it to 5x plus 3.
But for the other one, because there's a negative or minus sign in front of it, you have to multiply both of, or everything in there by negative 1 technically, so it's minus 4x plus 5.
That's right. Minus 4x and a plus 5. Distribute the minus so that positive 4 becomes a minus 4. The minus 5 becomes a plus 5.
So the answer is x plus 8.
Let's see if Jacob's right. 5x minus 4x. I agree with 1x. And then we have a 3 plus 5. Did you say x?
X minus plus 8.
Plus 8, okay. There. Okay. Multiplication of functions. Multiplication is just algebraic multiplication. So, any questions before we go on to multiplication? Any questions over there in the peanut gallery? Mike, one day I want to raise that up. I want to get something like, maybe a 3-foot pedestal all the way across so that they're up higher and I can really call them the peanut gallery. So, f of x times, f times g, that just says take f and multiply by g. Well, we know f of x, they gave it to us, it's 5x plus 3, and notice I'm enclosing it in parentheses. And we're multiplying it by g of x, that's 4x minus 5. I said that multiplication of functions is just plain old algebraic multiplication. If I came in here today and just wrote 5x plus 3 times 4x minus 5, what would you have told me to do? How would I multiply these two binomials? Yeah, 4-letter word starting with an F. Foil first. Let's start foiling.
5x times 4x is 20x squared.
Okay, I agree. The 5x times 4x is 20x squared. Outer.
5x times negative 5 equals negative 25x.
I agree. Inner, the 3 times 4x.
That's 12x.
Plus 12x. And last.
Negative 15.
Okay, 3 times negative 5 is a negative 15. And then we're just combining like terms. Multiplication of functions is just plain old algebraic multiplication. So we have 20x squared. Negative 25x plus 12x gives us
Negative
13x minus 15. And finally, f divided by g. Oh, I need to move this up. Y'all should have called out. Tony's not here today to call out, raise the page, so I'm going to have to rely on y'all. Okay. they're using a fraction bar to represent a division, and usually algebraic division is more involved than addition, subtraction, and multiplication, but not in this case. There's the division sign. We have f of x on top. Well, f of x we know is 5x plus 3. And g of x is on the bottom. That's a 4x minus 5. So we'd look here and we'd ask ourselves, can it be factored? No, both the things are linear. There's no common factor. There's nothing we can do here. We're just stuck with 5x plus 3 over 4x minus 5. There's no way we can factor and cancel. There's the quotient. And let's come over here. Well, I'm going to punch these answers in. Okay. So let's see. I'm going to switch over and start punching them in. Let's see, what do we have? 9x minus 2 for f plus g, f minus g, that was x plus 8. F times g, that's a 20x. Remember, where do you go when you need an exponent?
Down there, Google.
Okay, down here, this third one, the gray box with the little blue box up there, it says superscript. They're just trying to sound fancy rather than saying exponent. Click. There's the square. What do I need to do before I type the minus?
Press left.
Okay.
Press right.
Do your right arrow to get out of the exponent, and then we have a minus 13x minus 15. Any questions there? Okay, y'all tell me, for f divided by g, what am I going to do first?
Fraction.
Okay, use the fraction bar from the hot button.
5x plus 3.
Okay.
And do right arrow for 4x minus 5.
I just click down there, but right arrow would do it, or down arrow, I click
5.
There. Any questions there? Now they want to know the domain of f plus g, f minus g, f times g, and f divided by g. Realize both of these functions are linear functions. It just y equals mx plus b. mx plus b. These are lines, slanted lines. What did we say the domain of a slant? Actually, we made an observation when we were working with lines that the domain and range of lines is always the same thing. What numbers can we plug in for x? Remember when we were looking at domains, there are two things we want to avoid. We're trying to avoid, as far as domains are concerned, you want to avoid a denominator of 0, a number divided by 0, that's undefined, and we want to avoid imaginary numbers. You don't have any imaginary numbers sitting on the x-axis, so how do we create imaginary numbers? We need a special symbol for that to happen. You need a square root, and then the thing underneath it to be negative. Let's look at f plus g, f minus g, and f times g. Do you think, as you look through the work, look through all of that work that you just did for f plus g, f minus g, and f times g, are we going to pick up any denominators of 0? No, because nowhere do we have what? Starts with an f, and it's not fractions. There are no fractions, so there's no way you're going to get a denominator of 0. What about imaginary numbers? What do you need to have in the function to create imaginary numbers? A square root? Do you see any square roots anywhere here? No. So f plus g, f minus g, and f times g all have the same domain. That domain is the set of all real numbers. They're linear, that's a quadratic, but once again, no square roots, no fractions, therefore you can't possibly get an undefined result or an imaginary numbers. Oh, by the way, I'm reminding you, this is what we're trying to avoid. Denominators of 0 and square roots and negatives. Now, f divided by g. This one will have a different domain. So looking at this domain, I see that we have a fraction. We know we want to avoid a denominator of 0, so 4x minus 5 cannot be 0. So that means 4x cannot equal positive 5. So in that event, x cannot equal 5 over 4. So that domain, you can plug in any number you want to for x, any real number, except for 5 over 4. Could you plug in 1,000,000? Is 1,000,000 in the domain? Yes, it is. The only number that's not in the domain is 5/4, and I like writing that domain out in words. So for this f divided by g, I'd say all real numbers except 5/4. Oh, I gotta go. Hold on. I'm going to zoom there. All real numbers except 5/4.
And so don't forget to drop down the 2 on. Remember you could click the thing to make it go away.
Oh, I can do that. Thank you, Jacob. There. Okay. But they're not going to let you write out the words all real numbers except 5/4. They want that domain in interval notation. How would you say that? Here's 5/4. We don't have that number, but we have everything over here and everything over here.
Negative infinity, positive infinity.
Okay. Well, first of all, are we going to have any brackets in the interval notation?
No.
No, we're not. So, negative infinity to positive 5/4. Wait a minute. Jacob, what did you say? I agree with your negative infinity.
Oh, negative infinity, comma, 5/4.
Okay, you can't.
Then u, that you think, then parentheses, 5/4, comma, infinity.
Okay. So, why did we have to split it up? If we had just said negative infinity to positive infinity, we would have been including what number?
5/4.
5/4.
But because we put parentheses around it, it means that all numbers except.
That's correct. Okay, we're going to have to come and type these answers in. Okay, the domain of, remember f plus g, f minus g, and f times g, those domains are all real numbers. So parentheses, negative infinity, where is that thing? Excuse me, where I can't see my mouse.
It's on
there
the
it is.
very bottom.
Negative infinity, comma, infinity, right parentheses, and then I'm going to, I rarely do this, but since I'm going to have to type that thing several times, I'm going to copy it. So for f minus g, and f times g, and f divided by g, that's the one, that's the two disjoint intervals, parentheses, negative infinity, comma, 5. Let's see, 5. Oh, wait a minute, I'm typing a fraction, aren't I? 5/4. get out of that denominator before you type your parentheses, union, parentheses, 5/4, comma, infinity. Is that what I wanted to type?
Yes.
So check.
You got it wrong somehow. I don't know why. Just a thought kept on coming into my mind of like we did like this long equation, and when you type it into the answer and click check, it's just wrong.
Oh wow! I hope that doesn't happen. Okay, number 2. This is the second topic here in this assignment: difference quotients. Let me write this down. Switch over. Okay. The difference quotient has applications in calculus. Part of the definition of derivative, to be exact, it's f of x plus h minus f of x all over h. Now, we don't have to worry about any of the calculus aspects of the difference quotient. All we have to do is reduce difference quotients, okay? If you have to take calculus, your calculus teacher will teach you the calculus involved with the difference quotient. Remember how function notation works. That says go to f, and wherever you see a variable, replace it with x plus h. So keep that in mind. We come over here, number 2. They give us the function f of x is equal to x squared minus 2. And they have 3 things they want us to find. F of x plus h. And then, what we just found, f of x plus h, they want us to subtract off the original function f of x. If you understand what they're asking for in this part B, when we get to it, you'll be able to get that part B answer without showing any work. Then you're going to take what you found in part B and divide it by h. Notice the way it's stepping us through. Once you find part A, you use part A to answer part B. Once you find part B, you use part B to answer part C. And even when we're using when they don't give us these 3 steps, that's still the way that I simplify a difference quotient. Notice number 3. They just say find the difference quotient. They're looking for that final answer, not those 3 steps. I still go through the 3-step process that they use here in step 2. As a matter of fact, in my business calculus class, when I'm working with the definition of derivative, I first of all find f of x plus h, then I subtract off f of x, then I divide it by h. So these 3 steps, that's how I'll be simplifying them. Okay, let me switch over to my here, there. Okay, first thing they want us to do, they want us to find f of x plus h. That says go to your function f, and wherever you see a variable, replace it with x plus h. So in place of that little black x there, I'm going to write an x plus h. It's 2 terms, so I'm going to have it enclosed in parentheses. Replace the x with x plus h. You have something else stuck on there. What do we have stuck on there?
The minus 2.
Okay, the minus 2. I agree. Here's where people usually make the mistakes. They square the x and they square the h. That is not how you square a binomial. I remember this problem, coming up in the second section, the second homework assignment, when we had 3 plus 2i and we needed to square it. If you have a sum or difference being squared, what do you have to do? write it out twice, okay? So that's x plus h times x plus h. Here's my scratch work. X plus h times x plus h. And once I write it twice, FOIL it out. First,
x squared.
X times x, I agree with x squared. Outer x times h is xh. Here's what I'm going to do. If I have a term that has two different letters, I'm going to write those letters in alphabetical order. You'll see why in a moment. So x times h I'm writing as hx plus inner another hx. But always writing those things with multiple variables in alphabetical order, you easily spot the like terms. If you had xh and hx, you might not recognize those as like terms. And last,
H squared.
H squared, I agree. So we have x squared, hx plus hx. How many hx's? 2hx, I agree. Plus h squared. Any questions there? Now realize if that had been a cube, we'd have to have a third one and go through multiplying by h, go through multiplying by x, and combining those terms. So I think of myself as an optimist. No matter how bad things are, I always think, it could always be worse. So yeah, it could be worse. There could have been a cube there instead of a square. So before you sigh about having to square that x plus h, it could always be worse.
It could also always be better.
Oh, it could always be better. You're right. Okay, so I'm going to replace the x plus h quantity squared with what we found here. X squared plus 2hx plus h squared, and I still have what stuck on there? The minus 2. Now, they want us to find...
Well, we don't know that.
I remembered the instructions.
We just want to make sure,
Yeah.
that first off that we got the right answer.
Oh, so you're doubting us. Oh, you want me to punch it in right now? Okay.
Yeah,
X squared.
Everything, don't you know?
Oh, I didn't know that. 2hx
Just making
plus
sure that
h. Your confidence in our abilities is overwhelming, Jacob. Is that what I wanted to type in?
Yes.
I just want to make sure that we're doing it before,
See?
everything else, in case it was wrong. So,
Okay, you're right. Back in the olden days with paper...
He's the professor.
Oh, well.
He knows everything.
Okay, well, here's the thing. I remember back with paper books, I'd be going through working a problem, and as soon as I finished it, there'd be this huge rustle of paper, the entire class turning to the back to make sure that the answer was correct. I was like, wow, y'all have a lot of faith in my abilities.
Wait, so this
But
one is going to be literally just adding
if you understand what it's saying, you can get the answer without showing anything. It's a question of what is that saying algebraically. It is saying, take what we just found in part A,
then minus
and
x
minus
squared minus 2.
the original function. That minus is acting like the old-fashioned minus. When you were in elementary school and you learned about minus, that was take away, wasn't it? 5 take away 3. It's acting like a takeaway. So here's f of x plus h. You want to take away the terms that are in the original f of x.
So would that technically be 2hx plus 2 squared, or plus h squared?
I agree. You're taking what you have here. Take away the x squared. Okay, that's gone. Negative 2 minus a negative 2. You're taking away, that's gone. So all you have left is 2hx plus h squared. Question. Let's hear the question. What was it?
She was saying that
No,
she...
he literally just...
the negative 2 minus the negative 2. That became a negative 2 plus 2. Think of it as takeaway. You are taking away the terms from the original function. What you have in part A, take away the terms from the original. Here's something you'll want to notice. Every term that remains contains must have what letter?
H.
An H. So that's something you'll want to remember. Every term that's remaining, once you subtract off the original function, you'll have the terms left over that have an H. So just to check and make sure that the answer is right. Okay, so that's a 2hx plus h squared now part C. They want us to take what we just found and divide it by h.
So would it be technically 2x plus h?
Let's see. Part C.
Part C is 2hx plus h squared divided by h.
All divided by h. That means you take what we just found here, 2hx plus h squared, and divide it by h. You can't just start canceling because this thing up here isn't in factored form. What you could do is you can say there's a common h that we can factor out. You can take out that common h. What am I going to have here in the parentheses? I'm taking out 1h. Wait a minute, I couldn't hear you. What? 2x plus,
H.
what? And you had 1h remaining.
So that's the answer, 2x plus h.
Cancel the common h to give you 2x plus h. Any questions? Yes. This f of x plus h is saying go to your function f and replace the variable you see there with x plus h. Whatever's inside the parentheses, that's what you replace the variable with. Did I answer your question? We're going to see another one in a moment. Let me type this in. That's a lot of what?
Figuring out.
Oh, I guess it is, but I think the next one's going to have more figuring out. I'll tell you right now. I think the next one's going to have even more. Notice they say to find the difference quotient and simplify it, but they're not having us break it into 3 different pieces. I'm still going to break it into those 3 pieces. I'll find f of x plus h. Like we did in number 2, I'll find f of x plus h. Then I'll subtract off the original. The last thing I'll do will be to divide. So let me write the problem down. This is number 3. Okay. And switching over to where I'm writing. The long part of this is part A, finding f of x plus h. So the A part, f of x plus h. That says go to f, and wherever you see a variable, replace it with. So there are 2x plus h's. There are 2 variables, so we're going to have 2x plus h's. You have to replace that first x with x plus h. And I have to replace that second x with x plus h. And I have something else stuck on there, a plus 7. I agree.
Don't you hate it when plus 7 just dangles it?
Yeah, well, that's going to disappear in the next step. Now, I've already written out what x plus h squared was. How did we get that? Can I remember up here? We FOILed out. Well, what are we going to have to do with that 3 that's sitting in front?
Multiply it by the x.
So, here it is. We have that 3 sitting there in front.
So it's 3x squared.
So you're distributing. I agree. 3x squared.
Plus 6hx.
3 times 2, I agree with 6hx, plus
3h squared.
3 times h squared is 3h squared,
Plus 6x plus 8, 6 plus.
Okay, so, and so I was going to say, what are we going to do to remove these parentheses? I think Jacob was doing it here. 6x plus 6h.
And don't forget your dangling plus 7. That's it.
Any questions there? Yes.
On 3 parentheses x plus h, and then it says 3x squared, how come it's not at h?
It is right there. Look back up here. The x plus h squared, we wrote it twice, x plus h times x plus h. We FOILed it out and got x squared plus 2hx plus h squared. Now we have a 3 in front of it. So we distributed the 3. 3 times x squared, there's the 3x squared. 3 times 2hx is 6hx. 3 times h squared is 3h squared. I hate to say this, but I think that the best results occur when you don't keep rewriting the x plus h times x plus h and foiling it out all over. You've done it once. Use what you have already written there. Okay? And then that 3 is distributed across. Any other questions there? Part B.
Part B is
Okay.
like the
Oh, wait a minute. I guess no, we don't have to write in the answer. They're only looking for the final answer, the difference quotient. So we have f of x plus h minus f of x.
So we just minus what we got from the first one. We minus 3x squared plus 6x plus 7.
Okay, so we're taking away the 3x squared minus 3x squared, the 6x minus 6x,
And the
7 minus 7. You're taking away the terms from the original function. So this thing is gone,
the
the 6x is gone,
plus 7.
and the 7 is gone.
So the answer is 6hx plus 3h squared plus 6h.
Any question on our logic there? This is saying take the part A, the answer in part A, and take away the original terms. We took away everything that was up here in the original function, the 3x squared, the 6x, and the 7. Any questions? If you understand what that is saying, you can get that response without showing any work. Now part C. Part C, we're finally ready to get the difference quotient. We're going to divide by h.
So the answer would be 6x plus 3h plus 6.
I agree. Now, rather than putting it all over h and factoring and canceling the way I did here, There were only two terms up there. It wasn't too messy to factor and cancel. But remember, dividing by h is the same thing as multiplying by 1 over h. So what we can do, the quick way to perform that division, just put everything over h and cancel the fractions individually.
So the 6x
So you have a 6x,
plus 3h plus
cancel an h above and below for 3h, and plus 6.
that's the answer.
So even though this function was considerably messier, had a leading coefficient other than 1, had a unsquared variable term, it wasn't, the work itself wasn't that involved. The longest part of the problem is what? That A part, finding f of x plus h. That'll always be the longest part for you, okay? But once you've done that, you drop off the original terms and then divide by h. The quickest way to divide by h is just put every term over h. And this is the thing they want us to type in. 6x plus 3h plus 6. 6x plus 3h plus 6. Any questions there? Well, there are 3 topics in this section. Operations on functions, difference quotients, and composition of functions. Composition of functions is the stuff that we have the most problems to work with, because it's a whole new concept. It's really just repeated function notation, but still, I'm going to define composition of functions. This is an operation. There's not one just in terms of real numbers. For real numbers, the operations are addition, subtraction, multiplication, and division. This is an operation that's exclusive to functions. It's called composition of functions. Okay, here's the definition. Oh, and we need a little symbol. We need a symbol. You know, you use a little T to represent addition. You use a dash to represent subtraction. You don't use any symbol if it's going to be multiplication, but we need something for composition. Here's what they came up with. F composed with the G of X. And it's a little O. That little O is for off. My brother calls this stuff fog and golf, because we had a professor at SFA that did that, and it just annoyed the heck out of me. I really must have but you know, he knows he can say that just to, don't say that, say F composed with G, Tony. Because he says it, I remind him of Bree Vanderkamp from Desperate Housewives when I'm so, oh, don't do that. But anyway, F composed with G of X. That's saying take G of X and plug it into F. It's defined to be F parentheses G of X. You're taking G of X, the function G of X, and plugging it into F for every variable. And the order in which the functions are written is significant. If you had G composed with F of X, that would mean G is on the outside and F of X is on the inside. You're taking, in this case, you take F of X and plug it into G. It's not as bad as it sounds. We're going to evaluate, we're going to find compositions of functions at numbers, and then we'll find compositions of functions at variables. A composition of two functions at a number will be, we'll give a final answer that's a number. Okay, let me write this problem down. F of X is equal to 2x minus 1. And, oh, it's not g, it's h of x. Okay, I said that you can name your functions anything you want to.
Instead of golf, it's half.
Yeah, instead of golf, it's half. They want us to find h composed with f of 4. Let me write all this down, then I'll switch over to my... There, hold on, there.
So we replace so first we replace the x in the f of x with 4. So
Okay.
it'll be 2 times 4 minus 1, which equals to 8 minus 1, which equals 7.
Okay, so I was following you at the beginning. You said you've replaced the x in f with 4. You're looking at f of 4. Okay, f of 4. You come here, you replace the x with 4. So that's an 8 minus 1, which means
It's 7.
we have h of 7. Composition of functions, I hate to say it, it's one of those things where students have the best success when they don't try to write down every single step. This is saying f of 4. You know how to find f of 4. You go up here, plug in the 4. 8 minus 1. So in place of that f of 4, you have a 7. What is this thing saying to do? We know how function notation works. What is that saying to do?
Replace the x in hx with 7.
So we come up here to h, replace the x with the 7.
And because it's a negative
There's-
x, it will be a negative 7 plus 1, which equals to negative 6.
I agree.
So that's the answer.
We took the 4, we plugged it into f, that gave us a 7. We then take the 7, you plug that into h, negative 7 plus 1 gives me a negative 6. Any questions? Any questions over there in the peanut gallery? No?
You just need like one of those like studio things that just has like applause, laugh, cry.
That's what I
on
need.
it.
That's what I. Well, I don't want anyone crying. Okay, no, I don't
Isn't
want
that
to.
right, peanut gallery? The laugh sign just talks about.
Oh goodness. Okay, I'm not going to do this number 5. When we were looking at functions, I made the. We saw functions in terms of graphs, we saw them in terms of tables, and we saw them in terms of equations, and that's what we work with most frequently in this course, or equations. But I have a problem that I want to do that's just like your number 5, if I can find it. It's better than your number 5. Let's see. Where is it? Okay, here it is. I have a good function right here. This is just like y'all's number 5. I have 2 functions. Okay. With the function f, 3 is assigned to 7, 7 is assigned to 4, 9 is assigned to 2, and negative 5 is also assigned to 2. So the domain is 3, 7, 9, and negative 5. The range is 7, 4, and 2. Then we have another function. This other function, g of x, seven is assigned to 9, negative 5 is assigned to 3, 9 is assigned to 7, and 2 is assigned to 8. want to find 4 compositions. Let's see. How about I'm going to find F composed with a G of 9. That's the first one I want to find. And then G composed with F at 9. F composed with a G of negative 5. And G composed with F of negative 5. Let me make sure F composed with G at 9, G at 9, F composed with G. Okay. I remember evaluating functions using tables back when we first saw functions, and you got the hang that this number was x, and that function there was telling you which, what function you're using to find the y value. So I think I'll circle it like this. G of 9. We're working from the inside out. G of 9. That says go to the table G. What number is 9 assigned to? You go to G. 9 is assigned to 7. So we have F of 7. G of 9. You go to the G table. 9 is assigned to 7. You still have that red F out there. That says go to the F table. 7 is assigned to... I agree. Now the x value is 7. 7 is assigned to 4. Don't use this 7 and go backwards. The number inside the parentheses, that's now x. F assigns 7 to 4 for my final answer. F of 9. Look here. G composed with F of 9. We want F of 9. Go to the F table. 9 is assigned to
2.
We go to the F table. 9 is assigned to 2. So you have a G on the outside, and you have that 2 on the inside. Now this says go to the G table. 2 is assigned to
8.
2 is assigned to 8. Any questions there? F assigns 9 to 2. G assigns 2 to 8. What about F composed with G of negative 5? What table are we going to use first? For this one here, which table will we use first? F or G?
G.
G, that's that second one. We're going to look at G of negative 5 right there.
Which is 3.
Okay, you go to the G table. Negative 5 is assigned to 3. So we have F of 3.
And 3 on the F table is equal to 7.
Okay, now we go to the F table. 3 is assigned to 7. Any questions on our logic there? One more. Which function are we going to use first in this one? Okay, so we're using the F table. F of negative 5. Go to the F table. Negative 5 is assigned to 2. So we now have G on the outside. G is still there. F of negative 5, y'all said was 2. Now we go to the G table. Using the function G, 2 is assigned to 8. I agree. Any questions? Okay. So, I bet y'all can tell me these answers here. F composed with G of 3. What function do we use first?
The G.
G, 3 is assigned to
4, and
4.
then we do on the F table, and 4 is assigned to 6. So the answer would be 6.
That's right. Oh, there's only one problem per part. Oh, okay. Let's do. Oh, I like
one's
this.
9. That one's 9 because it's first saying find where it's registered for 8, which is 11. Then it says do it again, find 11, and it's assigned to 9. So the G table is completely irrelevant.
That is right. You do not need to use G in this case. You're only using F repeatedly. It says, first of all, use the F function. 8 is assigned to 11. And then, using F again, what number is 11 assigned to? 9. Okay. No wonder I like my made-up problem better, because there were more parts to it. I didn't realize 5 and 6 only had one little part. That was mighty short. Okay. Going back to what we were saying, a composition at a number gives you a final answer. That's a number. If it's a composition at a number, the final answer is a number. If it's a composition at a variable, you expect the final answer to be a variable expression. Here they're giving us two functions. This is number 7. Number 7, let me write them down. F of x is equal to 7x minus 8. And g of x is 10 minus 4x. 7x minus 8 and 10 minus 4x. Oh, maybe I should have written down what they wanted us to find. Oh, find f composed with g of x, and then g composed with f of x. Okay. F composed with g of x and g composed with f of x. So the first thing, f composed with the g of x. I know what g of x is. G of x. There's no number to plug in. We know what g of x is. It's that 10 minus 4x. So we have the f sitting on the outside. F is sitting on the outside, and on the inside we have the 10 minus 4x. So what is this algebraic notation saying to do? It says go to the function f, and wherever you see a variable, replace it with, it's 10 minus 4x, okay? So we go to f, where we see a variable, we're going to replace it with that 10 minus 4x. So that's a 7. Replace the x with 10 minus 4x. And we still have what stuck on there? That minus 8. Okay, good. And we know how to simplify this. We know what to do when we have parentheses with a number sitting in front of it. What's that going to give me? What am I going to do here? Distribute, I agree, to give me 70 minus 28x, and I still have that minus 8. Okay, I agree. 70 minus 8 is 62 minus 28x. Now they want the reverse composition, g composed with f of x. We know what f of x is. Right there, the inner function is f of x. We know what that is. There's no number to plug in. F of x, they gave that to us. It's at 7x minus 8. So we have g on the outside. Replace the f of x with 7x minus 8. So now tell me in words, what is this notation saying to do?
So it's 10 minus 4 times 7x minus 8.
I agree. It's saying go to g, and wherever you see a variable, replace it with 7x minus 8. So we have the 10 minus 4. This x here is what we're replacing with 7x minus 8. Remember your order of operations. What do you do first? Multiply or subtract?
Multiply.
You multiply. Do not subtract the 10 minus 4 and get a 6. You distribute the negative 4 over the 7x minus 8. So we're going to have a 10 here. Minus 28x, I agree.
32.
Plus 32, I agree.
It's going to be 42 minus 28x.
Okay, so 10 plus 32, I agree, but the final answer of 42 minus 28x. Any questions on our logic there? They said plug f of x in place of x into g. F of x was 7x minus 8. We come over here, replace the x with 7x minus 8, and then it's a matter of simplifying. Any questions before I punch these answers in? Okay, while I'm punching in these answers, I want you to be thinking about this question. Operations are classified either as commutative or not commutative. Addition is commutative. A plus B always equals B plus A. A multiplication is commutative. A times B always equals B times A. What about subtraction? Is subtraction commutative? Does A minus B always equal B minus A? No, it doesn't. What about division? No, it's not commutative either. A divided by B does not equal B divided by A. So here's my question. This new operation we have, composition, is it commutative? No, it is not. F composed with G did not equal G composed with F. If you mess up, let's say on a test they ask you to find F composed with G and you give G composed with F, odds favor, occasionally the compositions will be equal, but certainly not always. It's very rare for F composed with G to equal G composed with F. Composition of functions is not commutative. Oh, I forgot to write in the answer, didn't I? Okay, let me type in these answers, just so y'all know that I'm not just making this stuff up, that Pearson, my lab, agrees with my answers. Oh, yeah. Oh, that'd be funny, wouldn't it? 42 minus 28x. Now, Mike, you've realized that everyone's problems are different. So I'm not just standing up here doing everyone's homework and they just go type them in. They're all different problems. Each student, from class to class, when Tony and I go through these lectures, problems are always different. Okay. This, you will sometimes. So either they're algorithmically generated, those numbers, but not very often, and certainly not on tests. They give us two functions again. F of x is a linear function, g of x is the square root function. They ask us to find f composed with the g of x and g composed with f of x. I like this problem. It really does seem to make a point of how this ordering works, starting with f composed with the g of x. So we have g of x. G of x is on the inside. We know g of x is the square root of x. So we have f on the outside and the square root of x on the inside. G of x, we replace with the square root of x.
So it's 9 square root of x plus 7.
Okay, so you went to f, where you saw that variable. You're going to write in, replace that x with the square root of x, and you still have that plus 7 stuck on the outside. Is that plus 7 underneath the radical?
No.
No, so you need to make sure when you're typing in this answer, you don't put this plus 7 under the radical. Any questions there? Let's go in the opposite direction. G composed with f at x. That says f of x. F of x is on the inside. F is on the inside, and we know what f of x is. They gave it to us. It's 9x plus 7. So we have g on the outside, and on the inside we have 9x plus 7. So what is that saying to do? What's this function notation saying to do there?
Under the square root.
Okay, so we're going to g. Wherever we see a variable, replace it with that blue 9x plus 7, so we have the square root. And realize the plus 7 is under the radical.
You forgot the 9.
Well, I forgot the 9, didn't I? I forgot the 9 there. That plus 7 is under the square root in this answer.
That's the answer. And them's the facts.
Any questions there? Okay, so going. We have 9. We need a square root. Is this what I want?
No.
I don't want that plus 7 under the square root. Right arrow to get out from underneath that radical before you type in the plus 7. Any questions? Okay, y'all tell me, how am I going to type in this answer? What am I going to
Square
type?
root 9x
Okay,
plus 7.
so now I have the square root first, and the 9x plus 7 is all underneath that radical. Any questions? Let me write this down. Okay, so this is number 9. Let's see, are there I don't. Let's see. Let's see. We have only 13 questions today, so
That's easy.
well, we'll see.
I mean, this looks simple.
Let's see. And
We just replaced
and I was trying to finish this lecture by 3:30, and I think I'll be able to. Yeah. Is that it? Oh well, we may go a few minutes over, but I'm going to go f composed with g of x. Let me write this down. And they want g composed with f of x.
So the answer for that one, we just
What's the inner function first?
1 of x.
Okay, the inner function g of x, there it is, that 1 over x.
So it's f parentheses 1 over x parentheses.
Okay, I
Just
agree.
replace the x that's in the f equation with 1 over x. So it's square root of 5 times 1 over x, which we multiply the 5 by the 1 over x, so square root of 5 over x.
Okay, so that said go to f, replace that black x with the blue 1 over x. And remember how you multiply fractions. You don't multiply both of those things by 5. That's like a 5 over 1. So that's right. You only multiply the top. 5 times 1.
So it's equals to square root of 5 over x.
I agree.
Also, that 5 that you first made under the square root kind of looks like a 2.
The 5 that I first made, I guess right there it does, but this is a 5, y'all. I'm getting a little too, that's a 5. It's just that tail that makes it look like a 2. That's a 5. And I remember at the beginning of the semester we said we don't want fractions and we don't want under square roots and we don't want square roots and denominators. Well, that square root of 5 over x, that's the same thing as the square root of 5 divided by the square root of x.
So that's what we write?
No, we still have a square root. The square root of a fraction is the square root of the numerator divided by the square root of the denominator.
So we square both of them, so it's 5 over x.
No, we don't square. Who remembers? We do something. We do something down here involving that square root of x. The process was called rationalizing. Not square. Well, in a way we would square, because what we would do is we'd say, okay, let's multiply the square root of x.
By x? By the square root of x.
It's got to be the square root of x over the square root of x. Whatever you multiply the denominator by to maintain equality, you have to multiply the numerator by that as well. And the square root of x times the square root of x is equal to
X.
just x. 5 times the square root of x is the square root of 5x. There used to be a time when textbooks always said rationalize denominators. You never want to leave a fraction under a radical. You never want to leave a square root under a radical. But times are changing. Rationalizing isn't really that significant or that required the way it used to be. I believe my math lab will accept both of these answers, but if you view an example, unless they changed things recently, if you view an example, here's where they stop it at.
Do you want to test it to see?
Oh, well, I think we're trying to get through. And so, let's see. I'm gonna put in that first one with the square root, and then 5 over x. Y'all think they're going to take that?
We don't know.
Let's see.
Yeah.
And if you view an example, we got the other one. But
So isn't that one just going to be 1 over square root of 5x?
Okay, let's look and see. You see, they're leaving it with the fraction under the square root. So those old rules that you never leave a fraction under a square root, well, let's get into where books are sort of doing away with that rule. Here we have a fraction under a square root, and it's perfectly fine. I know one thing. I'd rather have to differentiate y equals 7 over x to the 1/2 power than that rationalized version. That would be what, 7x to the 1/2 all divided by x. But anyway, so I guess my point is, you can leave the fraction under the square root if you want. But I wanted to remind y'all of rationalizing. It's been a while since we've done it anyway. Now we need g composed with f. G composed with f. G composed with f. We're going in the opposite direction. We know that what's on the inside? I think g is on the outside. I think the inside function f of x. So we have g on the outside. We have the square root of 5x on the inside. And that's saying go to g, and wherever you see a variable, replace it with the square root of 5x. So we have a 1 over the square root of 5x. If you've rationalized it, you get the square root of 5x all over just 5x. But okay, we have a fraction. Hold on. We went to g, we replaced the x with the square root of 5x. So 1 over the square root of 5x. Coming over here, we have a fraction 1 over the square root of 5x.
Imagine they don't allow this, so, okay. It would be funny.
Any questions there?
No problem.
Number 10. For f of x equals 9x minus 2 and g of x equals 1/9 times the binomial x plus 2, find f composed with g of x and g composed with f of x. Then determine if their compositions are equal. Well, in most cases, do we expect their compositions to be equal?
No.
No?
But we never know.
The mere fact that they're asking that question makes me think that they might be equal.
They might be.
Let's see. Okay, number 10. We have the function f of x equals 9x minus 2 and g of x equals 1/9 times x plus 2, and we have f composed with the g of x. They want us to find f composed with the g of x. Y'all getting the hang of that substitution the way we're doing here? What's my inside function? Okay, there it is. It's that 1/9 times x plus 2. So f is on the outside, and on the inside we have 1/9 times x plus 2. So this says go to your function f and replace any variable you see with the 1/9 times x plus 2. So we're coming up here. We have that blue 9. We're going to replace that variable with that black 1/9 times x plus 2. Do we have anything else? We have that minus 2 stuck on there. Be careful with this multiplication. You multiply from left to right. It may look sort of messy, but as soon as you start multiplying, I think it's going to work out very nicely. You multiply from left to right. 9 times 1/9 is just a 1. The 9's cancel. So you're just distributing a 1 over the x plus 2. The fraction is gone. That's going to give us, distributing the 1, we're going to get, should be obvious, x plus 2 minus 2, which reduces to just 2 minus 2 is gone. We're left with just an x. Any questions there? F composed with g of x reduces to x. Now let's go in the opposite direction. G composed with f of x. What's going to be on the inside this time?
9x minus
Okay, f of x. That's 9x minus 2. So we have g on the outside, and on the inside we have that blue 9x minus 2. So this is saying, go to g, and wherever you see a variable, replace it with 9x minus 2. So we come up here. We have that 1/9. Replace the x with 9x minus 2. We have something else here. What is it? Okay, we've replaced that x with 9x minus 2. We still have that black plus 2.
But would it be in the parentheses like you're...
Yes, it would be, because it was in the parentheses here, so it's in the parentheses there.
So yeah, so it would cancel each other out. The negative 2 and the positive 2 will cancel each other out, so it's just 1 over 9 times 9x, which will equal to x.
Okay, 1 over 9 times 9x, you can cancel out that 9. You have 1 times x. The negative 2 plus 2 subtracted out for just a final answer of x. Any questions there? And they asked the question, were the compositions equal? What would you answer?
Yeah.
This is one of those times. In a no, it isn't going to be a couple of weeks. I guess next week we'll be looking at something called inverse functions. And the definition of inverse functions are two functions whose compositions reduce just to x in both directions. In that event, the functions are inverses. And there's some very nice properties about inverse functions, okay? But I'm getting ahead of myself. I'll say, yes, they are equal. So, okay, so x.
Good thing that the answer was just so simple that you could just type x, you know?
I know, and are they equal in this case? Yes, they were. Yeah.
The answer is x.
Number 11 is another one where they're having us check the compositions to see if they're equal. Now I want to go on to that one. 12 and 13 are review problems. 12 and 13, I don't remember what. You think you've got it? Okay. Oh, it's one of those cut point problems.
No,
it's 2 cut points.
You can always use the Math Learning Center if you get a very messy question.
Like question 11, for example.
Oh, let me look
What
at
the heck?
Oh, okay. You know something? We're going to do this. Mike's going to step out, but we're going to continue on. We're going to do this number 11. Thanks for coming over. It was really good to see you. Oh, goodness. f of x is equal to the cube root of 6x plus 5. Let me write this problem down. I didn't realize number 11 was going to look like this. I thought it was going to look like number 10. This one looks a little messier, so let's see. But we can get it done in 5 minutes. Minus 5, 6. Every 3 years, tenured faculty at every state-funded college or university must go through a peer evaluation process. Part of that is one of your peers has to be chosen randomly and sent in to sit in your class and write a little report. If y'all recognize Mike Wood from biology, he was, the person chosen to come into my class today. That's why Tony isn't here, because he was evaluating me, not Anthony. So, anyway, f composed with g of x. Let's find f composed with g of x. So, g of x is what's on the inside and what's on the outside. The f, okay, so f is on the outside and g of x is on the inside. 1/6 x cubed minus 5/6. And this says go to your function f. Wherever you see a variable, replace it with that 1/6 x cubed minus 5/6. Oh, this isn't going to be as bad as it looked at first glance. So we have that cube root and the radical. We have a 6. Replace that x. Oh, shoot, thanks. Oh, I'm here just talking and talking. Ah. So g of x is what's on the inside. And we know what g of x is. F is on the outside. So we're coming up here to f. Replace the x with 1/6 x cubed minus 5/6. I have something else stuck under that radical. What is it? That blue plus 5. It's hard to tell blue from black, but if you look on the YouTube videos, I can tell the colors there. It's just looking at this display.
With it having an x cubed, the cube root goes away, doesn't it?
Okay, well, first of all, before we do that, I think we need to deal with this multiplication. What's going to happen? What are we going to have to do with this 6? Distribute, and that's where it's going to work out nicely. When you distribute through that 6, 6 times 1/6, the 6 is canceled, leaving us just an x cubed minus, what are we going to get there?
30, so it will be minus 5.
Okay, the 6's, to me, I think of it canceling, cross-canceling the 6's, and you're still left with just that minus 5. Or you can think of it as 30 divided by 6, which still gives you 5. Then negative 5 plus 5
is 0,
So
so
just the x cubed, and then it's just going to be x.
What's the cube root of x cubed? I agree. The cube root of x cubed is x. What's happening here is that concept that we're going to see next week involving inverse functions. The cube root is the inverse of the cubing function. They're performed consecutively. They cancel themselves out. Now let's go in the other direction. G composed with f at x. G is on the outside and on the inside. F of x.
Cube root is 6x plus 5.
Okay. So now we're going to G. Wherever we see an x, we're going to replace it with that cube root of 6x plus 5. So we have a 1/6 replace that x with the cube root of 6x plus 5. And I think we have something else stuck on there. What is it?
Minus 5 over x.
5 over 6.
5 over 6, sorry.
And this is really working out nicely. What happens when you cube? Okay.
So we're just left with 1 over 6 parentheses 6x plus 5 minus 5 over 6.
Yes. We're going to have to distribute that 6, and I think it's going to work out real nicely. Here,
It'll be 6 over 6, so it's an x.
okay, so we have a 1x. 1/6 times positive 5 is going to be a positive.
5 over 6.
Positive
minus
5 over 6.
Minus 5 over 6, so it would just be x.
So they're gone, leaving us just with x. So even the messier function with the cube root and the cubing operation, they still both reduce to x. Any questions there? Okay. Well, I'll type in the XX yes just to be finished, but the last two are cut point problems. And now I know why I didn't put up to 15, because it looks like they're pretty long cut. They're the longer cut point problems.
It's the
And
fours.
yes.
The 4s be with you, the 4s be with you.
Oh,
Goodness. That was corny.
any questions there?
That was so corny.
Please remember to sign in. The other day there were 18 people here and only 8 people signed the attendance sheet. I know the attendance doesn't count for anything, but still.
I got to stop the recording.
Oh, thank you. Okay, I got to stop that.